Log on, tune in, find out. Another good idea from Cambridge.
I will continue the course. So these 7th and 8th lectures will be devoted to explaining the statement. It will take still quite some time. And then what I have thought when I prepared this lecture is that maybe it's good that I spend a lot of time on explaining the structure of the proof, because I don't know how far I will be able to go into every steps of the proof. For sure next time I will be able to make the computation for at least 2 important steps, but it's good to give the whole structure. So first let me recall what we have done so far. I've spent some time on introduction about the Landau damping phenomenon. We have spent some time on the mean field limit, and then on the Vlasov-Poisson equation itself, which is the model I'm using all along this lecture. And then we spent a lot of time on the linear Landau damping based on the study of the linearized Vlasov-Poisson equation. So in this part we have seen a full proof of the linear Landau damping and a full proof of the Penrose stability conditions in analytic spaces. And now we are in the nonlinear Landau damping section, which is about result and strategy, let's say, or global strategy. So, and then in this part, I will begin by recalling, so I think it was section 4, subsection 4, let's say, statements. I will begin by recalling the statements, so that I need to write it on the blackboard to be able to comment about it. So the detailed statement. So recall that, remember that the short, let's say, the understandable statement is the following. You consider the Vlasov-Poisson equation in a torus. D is the dimension, and you have some initial data F and some homogeneous profile F0 depending only on B. So these are the objects. So you have an homogeneous profile. Here is the, let's say, the short statement. You have a stationary analytic profile satisfying Penrose stability condition. Which I will denote by PCS, sorry. And an interaction potential satisfying that it's no more singular than Coulomb or Newton, which writes in frequency space like this. And the outcome is that F0 is stable in analytic topology. So it's a very short way of stating the result. Saying if you stay close to F0, you have some stability in some sense. And now let me write what it means. So this I will call it H0, because I want to comment on the assumption later on, so I will label them. And more precisely, what we assume are the following. So this H0 which is about really the structure of the equation. H1 is the assumption of the stationary profile, so I assume analyticity in the following way. I control the Fourier variable, Fourier decay by an exponential minus 2 pi lambda 0 eta, and it's a technical aspect in the proof, but for the moment don't think too much about it. And I also want to control the analyticity from a norm built as an entire series of the derivative, estimated in L1 Lebesgue space. So then, sorry, it's H1, this one. Then H2 is about the linear stability condition. So I assume Penrose stability condition on with an exponent, let's say lambda L, like for Landau. This is the Landau rate in the damping, which means, remember, we have this time kernel defined for time and for a given frequency k, which is obtained by this complex Laplace. We had done this last time. Okay. And this kernel should satisfy that for n xi with real part in the strip between 0 and lambda L lambda L k for any non-zero frequency, we want to see that the complex Laplace of this kernel at xi minus 1 greater than some constant that I called kappa in the course. Okay, so we avoid cancellation of the dispersion relation. This is really the study of Landau, of Penrose in the general case, Landau in the simplified case where F0 is a Gaussian. And H3 is the perturbative condition on the initial data. So we assume that the initial data is close to F0 in the following sense. So it's Fourier. Remember that in my convention, tilde is for Fourier in both variables always. Fourier is close to the stationary profile in this gliding estimate. We will see this a lot in the sequel. Sorry, it's not gliding at this point. So in this analytic estimate that we will use a lot, and this is very small. This is supposed to be very small, this epsilon. And second, so this measures the perturbation. This is the perturbation initially. It says that it's small in analytic regularity in X, analytic regularity in V, and also we ask that it's small in terms of its tail, velocity tail. So we ask an exponential velocity tail which is small. So for some beta, okay, for some beta here, strictly positive, we assume this quantity is small. So this is the maximum control we can ask. So this is for the estimate, and now for the conclusion. So any rate less than, strictly less because we lose a bit, less than the worth of lambda 0, lambda L which is here, and this lambda which is here. Maybe I should give it a name. Let's say lambda p for perturbation. So you see we have the regularity of the profile, the Landau rate, and the regularity of the perturbation, and we lose a bit. This is strict. there is explicit from the proof some epsilon 0 such that, which of course will be small, such that for epsilon between 0 and epsilon 0, we have the following. There is, first thing, maybe let's call it conclusion C, 0. There is a unique solution, global in time, and analytic, to the Vlasov-Poisson equation with initial data as we have prescribed. Okay, which is not trivial. This first conclusion is not trivial in itself. I emphasize that here I don't say that the bounds, the analytic bounds, are global in time. I just claim that I have a global in time solution. Then, first interesting conclusion is that we have the decay of the force field. So, let's say a user-friendly way to state it is the following. For any index L, we have that the force F at time t decay in the CL space, so in a very usual space. So it's a function of x only, and it decays like O of epsilon. So there is a constant. I don't want to write constant, so I write only like this. And O of exponential minus 2 pi lambda prime t. So the lambda prime which is here. So we have the decay of the force field. And in fact, if I put modulus around t, this is true for t going to plus infinity or minus infinity. And equivalently, I mean, well, let's say this is implied by the thing which we prove, which is the following: the density. So recall the density of at time t, rho of t is defined as a function of ft by its velocity average, and rho t minus rho infinity, and rho infinity is just the x average of rho t, which is time independence, and which is just the xv average of the initial data. Okay, the equation is a transport divergence free equation. You preserve mass, and then this is O of epsilon, the same in fact, like this. So you have convergence of the density toward its average, and the force, since it's a gradient of a convolution of the density, the force is going to 0. Okay, the constant term is not seen by the force because it's a gradient. Then, at now, no. Because it's, well, there is a more precise statement which I will give in a minute, but let's say it's nice to state like this because it is exactly the kind of thing you want to observe. I mean, usually, if you have an analytical norm, you don't know what it means, for instance, if you do numerics of experiments. This really means pointwise, then the pointwise of the derivative, and so on. So now I will give something more precise. In fact, we have more than the damping of the electric field. So it's electric of gravitational force field. The whole distribution Ft converges weakly towards some homogeneous distribution for time going to minus or plus infinity. The weak here, you could think to have something, let's say, easily defined. You could think to negative Sobolev space. But if you use this space, you don't see the good rate of this convergence. This convergence, in fact, has exponential rate, but in the following sense. In fact, if you would like to state this in the language of weak convergence, it is weak in the dual of an analytic space in V only. So that's a strange way of converging, but a much easier way to state it is to say that we have the gliding control, or the control like for free transport, as I called it in the previous course. Sometimes I also call this a cascade control. So at time t, the solution ft in Fourier minus the Fourier of the stationary state, which is not depending on x. So it's Fourier of a function constant in x, so you have only the zero mode in x. That's just the way to say this. And this, for any mode, this is controlled by O of epsilon, still the smallness parameter, exponential minus 2 pi lambda prime eta plus kt. And this is valid for anything k, t, eta, and t in R. In fact, if you want to be more precise, you could also control uniformly on this parameter some regularity in k only. You could also have minus 2 pi lambda prime k, but with no time decay on this one. There is no blow up in the x regularity. So, but so this is the key thing. It means a weak convergence. If you fix the frequencies you have and k is different than 0, you have convergence to 0. But it means something much stronger, in fact. And you remark that it's exactly the same thing we are trying to prove since the part on the free transport in the course. And also, we have that the x average. So in my notation, the bracket here always means x average in order to differentiate from the other things. The x average also strongly converges towards the same velocity profile. Okay, here the rate is not exponential, if I remember correctly. We will prove this also later on. So
the limit is not your original profile.
No, not at all. You mean the F0 or what?
Yeah,
Well, let's say you have two guesses, two naive guesses for what could be the limit. You could say it's the stationary profile, but this is not really reasonable for an Hamiltonian PD. There's no reason that you should converge to exactly the point around which you perturbate. Second, you could say, as in the linearized study that we have done, in the linearized study, in fact, the limit here was just the space average of the initial data. There was conservation in the equation imposing this. Here it's no more true, but I will comment about it. Yes, it's not. Oh, where?
Just the third. Yes.
Here, there's at this point there's no limit.
No, the other.
No. It's
Set 0.
here is the stationary profile. Oh, sorry. I understand the question. Yeah. Sorry. Yeah, it's a profile here. Okay, sorry. Yes. Yeah, that's what you mean. Yes. Yeah, okay, I understand your question, Simone. And the point is that what is different from the linearized study is that this is no more the space average. This is something different and which can be different from plus and minus infinity. Okay, so let me comment about this. Okay. Still, I'm thinking it's not even true, but if you put this is true for sure, like this, but with the stationary profile, it cannot be true.
some would say to convergence to the
Yes.
solution of 5.
Yeah, it would impose that the limit is yeah. Yeah, okay. Like this it is true. Well, another way to state it is that the solution itself would have this control without removing anything, and this implies, if you just take this implies that it has a limit, and then you can see what is the limit. Okay, so some comments about all of this. So first on the assumption. For H0, so first, I don't have pretty much to say except that condition that it decays at least. So, like, just, of course, it's for k non-zero. Remember that k is discrete. It's a condition of decay. This condition, this limit condition appears only in the nonlinear study. At least in our nonlinear study. If you remember, in the linearized study, you could go to even things more singular than Coulomb or Newton. And this, we don't know if it's just because we missed something in the method, or if it's something very deep. Of course, it is striking that it is exactly the most singular interactions that we see in the physics. And this limit is only occurring in the characteristic study. We will see this. H1. H1 is about the stationary state. Remark something is that we ask a lot of regularity, enormous regularity, but I don't ask Gaussian decay. I don't ask exponential decay in V. Meaning that this assumption allows, for instance, to very smooth polynomially decaying integrable distribution, which is something which is considered in the physics literature. So for the H2 assumption, so first we see that the time we spent in the last course was useful because we really do need the linearized stability condition, and you could reframe the whole theorem. One of the numerous ways to reframe it would be to say that we prove in a sense that linearized stability imply nonlinear stability in analytic spaces. With the serious, let's say, change of viewpoint, which is here. You have to take convergence in this sense, which is not usual at all. You could reframe it like this, and I just want to emphasize that for some this kind of question is exactly what people like Walter Strauss, who was here last week, are doing a lot, but they are doing this with much less regularity than we do. So in a way, their results are much stronger when they are able to prove them, because they don't need so much regularity as we do. On the other hand, I just want to emphasize that this is the first time that this linearized stability implies nonlinear stability has been proved for all functions satisfying for any possible shape satisfying the Penrose criterion. Again, with a lot of regularity, which is a drawback of the method. But for instance, something which was open for some time was to know if it was possible to show a nonlinear stability with a second bump, with two bumps. So this is the first stability, nonlinear stability result. Of course, two bumps satisfying the Penrose criterion for a double bump. Double bump, sorry. So meaning that if you have a secondary bump not too big, and still satisfying Penrose criterion, then you can run the whole machinery of the method. So in the words of this other group, this other team of people working, in the words of Walter Strauss, for instance, it would be like saying we have stability in this very regular space of F0 under perturbation with period less than T0, which is the critical period given by the Penrose criterion. Okay, this is not evident from the way it is written because we took another viewpoint from the very beginning. But the Penrose criterion, as I said, can be expressed as a criterion on the size of your box, which precisely means which is the period of your perturbation. Okay, then another different remark on this assumption is that analyticity, well, you can say that more or less you don't care about regularity, in application everything is regular, but still there is something a bit annoying with analyticity, is its non-locality aspect. By non-local, I mean the fact, the well-known fact that you cannot perturbate locally an analytic function. It is too rigid. It is a too rigid object. So every modification by a countable number of points will impose your whole function, because more or less these are generalization of polynomials. And so to get out of this, we want to get out of the so-called quasi-analytic class, which is the class of function which have this property of being determined, that the whole function is uniquely determined by anything done locally, because we want to be able to make a perturbation of our profile only of some compact small set. So this is the reason for the following variant of the theorem that we won't prove. I mean, the reason for including this variant in the paper is just what I wrote on the left.
Ma'am, before going to that, I have a question.
Sure.
Also to what was asked before. So then, what do you know about the relation between the F0 and the F plus and minus infinity?
That's one of the very nice perspective, which, I mean, more or less nothing, except that we made a very painful study in the end of the paper by making an expansion in the frequencies. Let's say you touch only some frequencies of your initial data in order to show that they can be different, which was something I will discuss this. It is theoretically extremely important.
By the way, the F plus and minus infinity are stationary solutions.
They are, of course, because they are homogeneous. So these orbits connect stationary solutions, and they can be different. But then, yes, then you have the very natural question. I fully agree with you, which is, I think, very interesting, would be to know what is this mapping, which maps some initial data towards this. In the words of people working, doing scattering theory for dispersive equation, it's exactly what they call this limit of the perturbed semigroup composed with the inverse unperturbed semigroup, and they go to plus infinity. This is exactly this mapping. F initial gives this is exactly this mapping. You could also imagine the mapping for all time. What is the mapping? F minus infinity gives F plus infinity, which is also the kind of scattering mapping.
But also the relation to the F tilde, I mean, to the stationary solution to which you are using the Penrose criteria, F0, not the initial.
Yes, on this we have an answer. This is analytically close to F0 with the same epsilon. So in particular, if epsilon is small enough relatively to Penrose criterion, we have not written this, but this is a question I thought about just last week. It should satisfy also Penrose stability criterion if epsilon small enough. If this is your question.
I mean,
Because
how-
it
how
is-
it's
it's-
related to the stationary solution.
Yeah, because it's analytically close to F0, and the analytic norm is largely strong enough to control the quantities in the Penrose stability criterion. You see my point? Penrose stability criterion depends continuously on the analytic norm. So for sure, that's a natural question. For sure, if epsilon is small enough, it will be also a stable thing. But for instance, to know how many of them are really different, of course, the natural guess is that it's a dance. It's even, in some sense, a full measure set of for which they are different. But okay, it's not proven. So let me state a variant. So let's say theorem prime. This is a Gevrey variant. So for some reasons that will become clear, I hope next hour or next week, we need something with regularity better than any fixed number of derivatives, than any Sobolev, any CK. So we use Gevrey. Gevrey means more or less that instead of having some decay in frequencies like this, you ask some decay in frequencies like this with nu strictly bigger than 1. And the good point with this Gevrey space is that they get out of the quasi-analytic class, but still it's extremely regular. So the variant just means you modify H3 into H3 prime. You ask that the perturbation is small in Gevrey regularity. And then the conclusions are modified as follow. C0 is the same. In C1 prime, C1 becomes C1 prime where the control becomes exactly as you could expect. Like this with alpha strictly less than 1 over nu. Note that we lose a bit, which is a loss qualitatively a bit stronger than before. Before we were losing only on the, well, okay, you see my point. But we did not try it by no means to be optimized here. And C2 prime is that, of course, then you modify the gliding estimate into this. Again with some alpha less than 1 over nu, strictly. Okay, so, and the nu here, we said that there is some theta strictly positive such that you can take, so one can take nu in 1 and 1 plus theta. Okay, 1 is exactly the analytic case, and then we can go to up to something. By the way, a very nice question would be the following: is this regularity correctly created for small time if you add some Fokker-Planck term on the right? If you have a Fokker-Planck term, then hopefully the mixture of the Fokker-Planck term with this awful nonlinear mean field, but hopefully, I don't think anything has been written in this sense, will be hypoelliptic. There are some hypoelliptic studies, for instance, by Hero and Pravda-Starov, which are quite optimal in a linear case, but here it's a nonlinear equation. And can you connect? Can you go up to the Gevrey regularity, which is produced by some small hypoelliptic term? And if yes, could we get rid of this by using the flow to make it appear? Well, that's. Could you use more or less that there are very few collisions, but they are smoothing the dynamics, but they are not able to drive the convergence to equilibrium very fast, but they are able to smooth quite fast, and then you can run the Hamiltonian Landau damping. Yeah.
Can you now say, I mean, after this, you state the theorem, so what is the definition of Landau?
Well, now mathematically I want to say that this is the theorem. But no, physically, the word of Landau is damping of spatial waves. That's where the word damping was taken.
So the first thing is that the dependence on x somehow disappears in the reading. So
exactly. This is the idea, the intuitive idea. If you let a confined plasma in a box, and if it's not perturbated too much, it will go back to homogeneity. It's also the intuitive idea, which is less clear to visualize, that when a galaxy is forming, it reaches quite fast at the astronomical time scale. It reaches very fast some situation where more or less visually it's stable, it's stationary in space. And
so we can say that your stability theorem is a stability theorem on the family of homogeneous solution, not on one particular homogeneous solution.
on the what, sorry?
On the family.
On the whole family of homogeneous solutions, which are first analytic and stable according to Penrose. Yes.
You said that doing numerics it's very hard to sort of see Landau damping conclusively. The smoothing effect, do you see that if you suspect it might be happening before? Like, is that sort of something you would expect from numerics, or you also can't tell?
Well, if you want to compare with something which is hard to see, it's also hard to see. But no, to see a smoothing, the smoothing probably it could be. I don't know. I'm not very expert in numerics, but I don't think I don't think anybody has tried to study precisely the Vlasov-Poisson-Fokker-Planck for the hypoellipticity. For other properties, it has been studied, of course, but
just to get an idea.
Because hypoelliptic theory and the followers of Hermander are much more focused on linear PDEs, and this is kind of awful. You have this mixture, but I don't know. Maybe somebody have tried. So, okay, now it's about the conclusion. So first thing is a bit an answer to your question. Decay of the force field is really what is called Landau damping by physicists. Let me just emphasize that it is extremely striking philosophically if you're a physicist, because in kinetic theory, that's just, let's say, a digression. In kinetic theory, the full distribution is not observable. So, I mean, the only thing you observe is the force, the electric field. What you observe is the electric field. So from a macroscopic viewpoint, from what you observe in your plasma, you see a relaxation to equilibrium. And this is the reason for which in astrophysics books, for instance, it's called non-collisional relaxation. Or in other words, relaxation with constant entropy. This is a relaxation phenomena on the field which is produced by Hamiltonian dynamics behind. And this has produced a lot of debate. The fact that you derive something on the electric field you can observe from an equation on the full distribution you cannot observe. About the second conclusion, this is really what was the goal of the theorem. As a bonus, you get this limit. So this opens all these questions about studying the scattering estimates. We prove in the last, the one before the last section of the paper, we prove that this is possible. It happens. Let's say it happens for some initial data. And so this has a lot of consequences, because observe that conserved all the structure, the invariant structure of the equation, we had discussed this 2 weeks ago, Casimir functions, energy. So remember, for this equation, the Casimir functions are function of this form. For some functional big F of F. And the energy is something like this. Plus or minus the energy of the force field. Okay, plus is for a plasma, minus is for a galaxy. It's focusing or defocusing in Schrödinger words. And this is kinetic and this is self-interaction energy. And maybe there's also 1/2, sorry. And these two quantities are unchanged by reversing time. Which means that these limits are not predictable by any variational principle relying on this kind of quantities. And this is somehow opposing to many interpretation and theory which has been built, the so-called statistical theory of for 2D Euler and for Blazor-Poisson. I mean, we have not proof for 2D Euler, but I'm pretty sure it's the same. It's an argument against the statistical theory of the Landau damping. It says more or less that even if you have a macroscopic relaxation, the equation still keeps full memory of all the detail of the evolution on the full distribution. I forgot just some remark on C0, a less important remark. This existence uniqueness result at the moment, I don't say it's necessarily difficult, but at the moment is not covered by any existing Cauchy theory. It's not covered by diurnal ions because we are by ions per time because we are in the torus. And it's not covered by Pfaffel-Moser because we don't have compact support. But well, that's just a remark. And now, still on the estimate C2, so that's something I had forgotten. Another way to state it is that we prove the following kind of estimate. If you estimate starting from F initial, that's one outcome of the theory. If you estimate starting from F initial, you follow the nonlinear semigroup up to time t, and then you follow backward the S minus T0 means free transport semigroup. 0 means you remove all the force. And then you follow backward free transport. Then, in usual analytic norm, it remains uniformly bounded. So it really says more or less that your dynamics remain around the free transport dynamics. And it's a kind of orbital stability in analytic sense, if you want. Okay, so then final comment before writing the scheme. Then next thing I want to write the scheme and discuss the strategy and let's say the different obstacles we have to solve in order to prove the result. Let's say I want to make some comeback or on the discussion of chapter 0 about irreversibility and so on. So how can we observe large time relaxation for reversible PDE? So there are two pictures that are nice to keep in mind here. First one is a picture I discussed, the picture of Boltzmann. I mean, the picture of how I understand the idea of Boltzmann of irreversibility. So this idea of factorization, remember? If you were here at the first course, I discussed how Boltzmann is arguing, if you want to explain his very famous formula for the entropy, the one which is written on his grave. So imagine omega is your very large phase space at a micro level. So micro is anything smaller than macro, and macro is anything larger than micro in my picture. And so you have some phase space here, and you have some region of the phase space which gives a macro state at time 0. And then you let things evolve up to some time t1, and still in your phase space your macro state evolves towards something mt1. You assume you have an evolution equation here, a macro evolution equation, which I write with the in the fact that I have a semi-group. And you assume that on the left you have an Hamiltonian evolution, which I write in the fact that I have a group. And here I have a volume preservation property because it's Hamiltonian. And if you can factorize, meaning if when you follow this guy here, this is also the macro state associated with any micro states which has evolved from this small ball. So this small ball is over here. Sorry, it's here. Same volume, and you want that all the microstates here are still associated with the mt1. This is a factorization property, and it can, of course, it can happen that another part of your phase space has also joined and has increased the volume here. And Boltzmann defined the entropy as S equals K log, if you call this omega of m, okay, from a macro state you define the volume of microstate associated. The entropy is defined as the logarithm of the volume in the phase space up to a constant. And okay, if you take a good convention of sign, usual one is that entropy grows, but you see that volume in my picture will grow. It can only grow, in fact. But there's an absolutely non-trivial things here, which is the what I call the factorization. And Boltzmann argues for the fact it's only true in the limit of infinite number of particles, and this is the molecular chaos debate and so on. But here I have done the picture because if we want to compare what we do, in our case, the micro situation is the full distribution of Vlasov-Poisson. The macro thing is the density, the spatial density. We have lost some information by taking some velocity average. The point is that, and that is why one of the reasons why the result is surprising, the point is we are able to show some irreversibility here, but without closing anything. There is no factorization in our case. And you can easily convince yourself that there could be no factorization. So what is different and what is still inspirative from this idea of Boltzmann? So difference is that here there is no factorization. What I mean is that there's no closed equation on rho. Okay, I'm just finishing with this. You cannot close an equation on the density alone. It will always depend on the velocity distribution initially. You can easily cook two velocity distribution which will give rise to two different evolution for rho. Even for free transport, it's completely wrong. But a common point, if you want, or a comparison, is that in Boltzmann ID, this factorization could only hold for very, very unlikely, rare, low entropy initial data, uncorrelated one. And here, we have a notion of rareness, if you want, which is provided by this very small analytic topology. So the picture of the theorem could be done like this, in a way, and we don't have a n goes to infinity in the theorem as well. You have some stationary state, regular, satisfying Penrose criterion. You have some small neighborhood in analytic topology. And if you start from some initial data in this neighborhood, you have convergence. At minus and plus infinity by the Vlasov-Poisson flow towards two stationary solutions. But the convergence is weak, and it can be either homoclinic or heteroclinic, depending on whether they are the same or different. And the density, now if we go to the macro world, if you want, the density is converging to the same thing. Okay? Still at the same time we have, so for the density we have a strong convergence in plus and minus infinity, and it converges to the same thing.
But rho infinity is not the density of F plus infinity.
Yes, it is.
Please.
But all the other, yeah, it is, but all the other Casimir are broken. Let me think. No, the mass, I think it is. But
But then
The mass is
sorry?
the mass is the one telling you that rho infinity is the density.
Yes, more or less the constraint of the mass is still is too big. I mean, yeah, it is the mass. Rho infinity is defined like this.
rho infinity
Is
you
the
define as the
is the x and v average of the solution?
it's the mass.
Yes, it's the
It's
real
same
mass.
initial data.
Yes,
So
yeah, yeah.
F plus infinity has
So
the
you-
same mass.
Yeah, I see your question. You don't have escape of mass at infinity.
Yeah, because you don't prove convergence. So you have this weak convergence in some subtle
It's
space.
true. Yeah, yeah.
It's not obvious.
No, it's not obvious that it. Yeah, you're right. But other functional,
You have the energy is bounded.
the energy will remain bounded, of course.
So at least in the plasma, I mean, in the electrostatic case, you automatically have convergence of the mass.
You can. Sorry.
In the electrostatic case, then you have a uniform in time control on the second moment. So if you have any kind of weak
Yes.
convergence, you have.
Yeah, that's. Yeah. You're right. You're right.
So not obvious.
Well, in gravitational case, it's not so clear because they have opposed sign. But I agree fully with you. Yeah. If this is a plus, then this is coercive in both terms, and you control the second moment. But another way to say is that this is always conserved, but as time goes, we see a shift of self-interaction energy towards kinetic energy, and this for more nonlinear f will not be preserved for t going to infinity.
Even the analytic norm that you have, you can probably control uniformly in time.
Oh yes, but I have given this, no?
So the second moment is all.
Yeah. No, this is rigorous. Oh yeah. What you mean? Yeah, sure. You can show rigorously this goes to 0, and all the energy in the end is in the kinetic energy. Yeah. So next I will discuss the scheme and the different things to be proved.
Okay, so let's resume in 20 minutes.